think we had some questions, but I think people are feeling a bit shy. So if anyone's feeling shy and doesn't want to ask online, then you can. I don't know what to do, but ask Subhajit or Franco.
I had some questions by direct message, so I did answer some of them, I guess.
Oh, okay. So you can direct message Pierre if you're feeling a bit shy. But yeah, I think there was a bit of confusion about something you wrote with the number of trajectories that hit your set K is a Poisson.
I'm losing you, sorry.
Can you hear me?
Yeah, no, yeah.
I think there was confusion about the statement that number of trajectories that hit K is Poisson intensity U capacity K. So maybe could you just re-explain that before we go on, please?
Well, I mean, so it's a statement. I'm not proving it. It's in some sense a defining property of this interlacement model that. So first of all, it's a model. It's a Poissonian model. So the number of anything that you can measure is going to be a Poisson random variable, and it just so happens that the number of yellow trajectories that hit the set K is a Poisson variable with mean or intensity parameter, which is, so then now some positive real number, lambda, and lambda is actually U times the capacity of the set. So from this, you can see, for instance, that if you crank up U, you get more trajectories, right? Because the intensity of this Poisson random variable goes up. And so because the Poisson is infinitely divisible, you can actually, if you have the picture at U and you want to get it at 2U, then you can just sample an independent Poisson U thing on top of it. And also, if you increase the set K, then the capacity also increases. And so you get more and more trajectories the more you grow K as well, which is also somehow sensible.
Yeah, that answers the question. Okay. So yeah, I think we can start with the final part of Pierre's mini course.
Okay, so I promised to you to show continuity of a percolation phase transition in higher dimensions, and that's what I'm basically going to do in this last hour. And I wanted to stress this idea of, there is this exploration from outside and from inside, and you see this all over the place. So you see this, for instance, very vividly in this paper by Hugo and Vincent, where they prove sharpness for Bernoulli percolation. And somehow, for this model that I'm discussing, these two methods of exploration, they somehow become optimal because you can combine them with the Markov property of the free field, which in some sense allows for things to be more precise. So we've actually already seen the exploration from outward a part of it. So this was, essentially this argument I was giving yesterday, and I will, allude to it a little bit later on. And so for this last hour, I want to show you how to explore things from inside. So, you explore clusters starting from a point, say the origin. Okay, so before we do that, I need to tell you a little bit about what are called cable systems. And so to do this, so let me slightly generalize my setup, and I want to talk about the concept of a weighted graph. So this is just a small generalization of what we've been doing. So, imagine that you have a piece of your graph. It's maybe still the same graph. And so maybe this point X, this is point Y. And before, I simply had weights 1 everywhere. And of course, so this just means that my random walk chooses its neighbor uniformly at random, but you could more generally replace 1 by some positive weight lambda xy, which is symmetric. And then, the effect this has is that the probability that the random walk goes, let's say it's in x at time n and it goes to y at time n plus 1, well, this is now simply proportional to this weight lambda xy. So it's lambda xy divided by the sum over the weights over all neighbors of X. Okay, so why am I introducing this? Because you can now somehow extend the setup that we have. And so you can do this in the following way. So of course, if I have this more general weighted graphs, I still have a Gaussian free field. And its measure formally is going to be, proportional to x of minus a half times this Dirichlet energy. So same as before. And just to remind you, this Dirichlet energy is, basically the L2 norm of the gradients. So in the discrete, gradients are just increments over neighbors. And you sum over all pairs of neighbors. Okay, and so this is, the right Dirichlet energy if you have, unit weights or natural weights. And in the general case, you just multiply this by lambda xy. So before all the lambda xy's were equal to 1. Okay, so I'm telling you this because you can now start to do the following. So you start with G equals G0, and my weights lambda 0 are just unit weights between nearest neighbor. And now you can define a graph G1 by doing the following. So, before my vertices were here, and now for G1, I keep my old vertices, but I also add the midpoints of every edge. I do this for every edge of my graph. And, if you know a little bit about network equivalence and Kirchhoff's rules, then you know that resistors in series add, and so these lambdas are actually conductances. So the right choice of a weight to put on these new edges, which are half as long as before, is actually 2, because their inverses should add up to 1 or a half, maybe. It doesn't really matter. So you put 2 everywhere here. So lambda 1 equals 2 between any nearest neighbor, and you can just iterate this procedure. So at step 2, you've been splitting them even more, and so for general n, you're going to have Gn, which has basically this edge chopped up into something like 2 to the n little pieces, and the weights are 2 to the n. Okay, and you should now think of this entire original what's it called, edge to have length 1. And when you cut things into pieces, so you should really think at scale 1 the distance between that point and that point to be a half, and then a quarter, etc., etc. And so what I'm getting at here is that actually, if you look at these graphs Gn, and you look at the Gaussian free field on them, so this is exactly the measure I have defined here, except that now the free field is going to live on the vertices of my graph Gn. So I have more and more vertices, and the weights here get rescaled. Well, then you see this actually converges to a limiting object as n tends to infinity, G tilde phi tilde. So what is this limiting object? So my limiting graph, so to speak, which is called the cable system, is simply my original graph, but now I think of having a sort of continuous interval of length 1 here and gluing it at both endpoints. So I have this sort of continuous extension of my original graph. And on it, I have a field which is still a Gaussian field, and it's continuous. And this is called the GFF on the cable system on G tilde. And there is a very, very simple description of this phi tilde. So you can simply observe that. So in the way I've set things up, if you restrict phi tilde to the original vertices of my graphs, which are now a discrete subset of my cable system, then this is still my original Gaussian free field. And that's because I did things in a sort of network equivalent way. And so now you can simply get phi tilde by first sampling the discrete Gaussian free field, so the one we've been talking about all along. So this is the free field, on these white points here. And then you just add independent Brownian bridges between them. So say, if you've sampled phi x here and phi y there, maybe this is the value of phi x, this is the value of phi y, so maybe make it green, then you just, sample a Brownian bridge between the two. Now, why is that? So I'm claiming that this is really nothing but, in essence, Donskoy's invariance principle. And the reason is, so, by the Markov property, you can essentially freeze everything outside of any given edge, and you can actually even take scaling limits edge by edge if you like. And now if you inspect a particular edge, so you see that the distances get rescaled by 2 to the minus n, right? That's how I should tell you, the distance between that point and that point should be of the order 2 to the minus n. And the conductances get rescaled by 2 to the n, right? Which, I mean, if you push it into this parenthesis here, is actually 2 to the n minus 2. So you have already sort of a, diffusive scaling happening here. And what I mean by this is, along an edge, you have something which in the increments looks like, phi t over square root of t, and here t just happens to be 2 to the minus n. And now, why am I saying that this is just Donskoy's invariance principle? Is because if you look along this sort of long one-dimensional chain, then actually you see this measure here factorizes. It's a product measure in these increments. And so the scaling limit will just be a Brownian bridge. Okay, so now the result of this is that we have accessed this cable system extension of the Gaussian free field. And the upshot of this is that this is a continuous field. So if I explore clusters in this field, for instance, when I reach the boundary, I will reach a very specific value. There is no discrete effects that come from jumps. Okay, and now you can define a percolation model, which is exactly the same that we've been studying before on the vertices of G, but now you define it on G tilde. So, okay, so how does that go? Well, you give yourself a parameter A and R, and you study excursion sets of this continuous extension. Okay, so these things are not going to be, discrete subsets of my vertex set anymore. They are, if I draw, for instance, a little piece of ZD here, and I think of it as my cable system Z tilde D, so I have really added these one-dimensional intervals and glued them through their endpoints, then, my cluster is going to be some random subset of this graph, okay? And so you can ask whether or not, these green, so everywhere on this green set, you will have phi tilde greater or equal to A, and in fact, the cluster stops every time you hit. So here at this boundary point, phi tilde is actually equal to A. Okay, now you can ask whether these things percolate or not when you vary A. And just to tie this into the model I defined at the beginning, so you may not like to think about these continuous objects, but actually if you look at the probability that some edge E, which I am now identifying with its corresponding one-dimensional interval. So the probability that an edge is completely contained in the excursion set. Well, what is this? Well, this is just the probability. So here I'm drawing my edge horizontally. I have maybe phi x and phi y at the endpoints. And well, if I want it to stay in the excursion set, then that means that if this is my value A, my Gaussian free field has to stay above this barrier A everywhere inside the edge. But I told you, if you give yourself phi x and phi y, then this here is just a Brownian bridge with, endpoint values phi x and phi y, and maybe normalized to have, variance 2 at time 1. There are nagging factors of 2, which I'm hiding under the rug, essentially because, if you have a little Brownian motion, say a Brownian excursion, or even a random walk excursion that starts at a point and comes back to it, then if you look at any typical point in the middle, it has to cross it twice. So, this is essentially where these vectors of 2 come from. Okay, so the probability that the edge is entirely contained in my excursion set, this is the probability that a Brownian bridge stays above the barrier A, and the probability to have this is, you can compute it exactly, is, so there is a little factor of 2 here, which I was missing in my first lecture. But I'm flashing this because this is exactly the model that I was considering here. And so the statement I was making about, decay at probability being governed by some critical exponent is actually precisely dealing with this model. Okay, and now you can really think of this as a discrete model, because if you ask questions about percolation, so whether or not you have an infinite cluster, you will be able to read by looking at just the edges which are completely contained in your excursion set. The only difference between the two are maybe little, remnants that, like you see in this picture over here, that do not entirely cross an edge. But for questions relating to, what's the decay of a connection to distance r, it's basically it's equivalent. Okay, so this is really a bond percolation model. You don't need to talk about the cable systems to define it, and that's exactly what I did in the first lecture. You can of course still exploit the cables, which is something that we will do. Okay, and so this idea of looking at the cable system, so this has a long history. For instance, if you know about the Carnot-Varopoulos bound, Varopoulos's proof of that, we use the cable systems, but in the context of the GFF and loop soups, it's really the merit of Lupu to have reintroduced this. So that's why I like to call this. Titus was looking at the loop soup, but here I'm talking about the GFF, but there are two faces of the same coin, so I like to call this model a la loop. Okay, so this is the model I want to now prove a theorem about. And so you can, fix a point 0 in your graph. So my graph is just transient, no further assumptions. And you can, for instance, define this order parameter theta of A, which is the probability that 0 is connected to infinity by an excursion set in the excursion set above level A. So this now really refers to the existence of a continuous path, that connects X to infinity. Okay, so so this is exactly the quantity that I was looking at in lecture 1. And so the theorem, which I'm going to write here, so it comes in 2 parts. The first part is that when A is, let's say, positive, then the probability that you are connected to infinity at negative levels is strictly positive. And in fact, this we already know how to do. You run exactly the same proof I already ran in the discrete case. So everything works, and you can actually, tighten the screws and get more out of the argument. But in the interest of time, let me not go there. So, this part of the statement is essentially follows from an exploration from outside. Okay, so this we already know how to do, nothing new under the sun. And so the next level that you might be interested in is A equals 0. And I already told you, if you rid yourself of this tilde here and you just look at the discrete excursion sets, then 0 is actually not critical. I mean, on ZD, the critical value is strictly positive. But it just so happens that, well, on many graphs, 0 is actually the critical point for this cable system percolation, and that's why my theorem in lecture 1 was actually dealing with level A equals 0. And so the precise statement, which is true on any transient graph, so maybe let me stress this here, is that if you look at the capacity of the cluster of 0, so this is the cluster of 0 in, and you can think of this, I mean, the statement is still true. Think of this as just all the edges, all the open edges, where open means what I wrote here, that are connected to 0. You look at this set. So the capacity of this set is finite, almost surely. So this is when A is equal to 0, and a fortiori also when A is positive, because it's monotone. Okay, and this second item here actually implies, in many instances, continuity of the phase transition. So this is just now a matter of deriving from this that actually theta of 0 is 0. And so this is true essentially if, infinite sets have infinite capacity. So this is true, for instance, on any graph such that the Green's function on the diagonal is bounded uniformly, which is, for instance, the case if G is transitive. Okay, and so that actually tells you that for this model, the argument that I showed you a la Brickman-Leibowitz mass that told you that, everywhere here you are supercritical, is actually in a sense sharp, because when you reach level 0, you actually don't percolate. So in this region here, theta of A is actually equal to 0. Whereas over here, so this theta of A is positive. Okay, so what I need to explain to you in the remainder of the time that I have at my disposal, so I think we still have half an hour together, which should be more than enough, is I need to explain to you how to prove this statement. Okay. So I told you this is going to go by essentially exploring the cluster of 0 starting from 0. So this is going to be an exploration from inside. This is one of several possible arguments that you can give, but it's one that has maybe a lot of analogy with Bernoulli. Okay, so I want to essentially study the derivative with respect to A of any connection events, and then feed this exploration from inside into this derivative. So let me make a little detour and actually discuss a differential formula for this model. This is going to be a Rousseau type formula if you're familiar with classical percolation. Okay, so the first thing I hope you will indulge me is I'm going to drop tildes, because if I don't, I'm going to forget them soon enough. And then, so phi tilde will now become phi, but by phi, I really mean the GFF on the cable system G tilde. So this is this continuous Gaussian field that exists on the metric graph extension of my original graph. Okay, so here is a lemma. So take any finite set K, and I'm going to look at, sorry, let me say that again. So K should be a bounded, let's say, compact subset of my metric graph. So, maybe take a finite subset of G and add all the cables between pairs of vertices inside that set. That will be good enough for our purposes. And so I want to study an observable F which only depends on the free field inside of K. So I'm going to write F below, but I think of F as being measurable with respect to my configuration, restricted to K. So it's sort of a finite volume event, if you like, which is measurable with respect to my percolation configuration. And I want to study derivatives, so, with respect to my control parameter, which here is A. So I want to study derivatives of things like the expectation of F. Okay, and the statement is that this is actually equal to F, but it gets multiplied by this weighted average of phi that we have already seen. So I'm not going to give you a full proof of this, but let me, try to make this statement plausible for you. And let me stress, actually, the statement in the way I've written it here is actually true on the cables, but it's also true if you just looked at the discrete Gaussian free field. And so the way to see this quantity here appearing is maybe as follows. So the way you can do the proof is, you want to take a derivative with respect to A here. Where does the dependence on A sit? Well, it sits in my argument here. But what you can do is you can just change variables. And so what I mean informally is that you replace phi by phi plus A. So you shift by A inside the region of interest. And then, if phi becomes phi plus A, then, this function is now a function that for my shifted field is above level 0. So there is no dependence on A anymore because these things cancel. But of course, when I do my change of variables, I'm going to pay some sort of Radon-Nikodym derivative. And now the dependence on A sits in this Radon-Nikodym derivative, and that's explicit, and you can take a derivative. Now you could, so the right way to do this is to use Cameron-Martin, but let me still do this in a kind of pedestrian way. So I already told you, right? If you have your set K and you want to shift the field by A inside of K, well, there's good and bad ways to do that. And the reason is that, if you shift by A inside of K and you don't shift anything outside, then, you're going to create these huge gradients here. And that's not a very smart thing to do. So actually, the optimal way to shift the field is to shift by A in the region where you want to get rid of A, which is K. There you have no choice. And away from K, you sort of shift harmonically. So really what I mean by this shift more formally is so really the optimal choice is to shift by, so let me call this A times H. So H was the probability starting from X that you hit K, which of course, if X is in K, is just equal to 1, but anywhere else will sort of decay in this sort of volcano type fashion. Okay, and so why am I telling you this? Because now, if you formally perform this change of variables, then you're going to end up with something like phi minus A, so plus or minus, it doesn't really matter, phi minus AH, phi minus AH, and you want to compute the Dirichlet energy of this. So remember, the energy is just the L2 norm of the gradient, and by Gauss-Green or integration by parts, this is just the same thing as phi minus AH Laplacian of phi minus AH. Okay, and now if you look at this expression, so of course you're going to have this phi Laplace phi, which is going to produce again Dirichlet energy of the form E of phi phi, and then you want to take a derivative in A, so you're interested here in particular in the terms which are linear in A, and these are these cross terms. So this sits in the exponential, but when you take the derivative, they get reproduced, and whatever depends on A, there is also a chain rule which is going to pop something in front, which is exactly what I wrote here. And so the linear term, the one that's proportional to A, reads what? Well, it's inner product between H and minus Laplace of phi. Of course, this Laplace operator is self-adjoint, so you can also commute it over here. So this is minus Laplace H phi. And now you might recognize, so you remember my probability to hit K. So this was the first lemma I proved in my second lecture. This you can also write as the sum over, the Green's operator acting on the equilibrium measure. Okay, and if you hit both sides with the Laplacian, then the Laplacian basically undoes this Green's function, is the inverse, and so minus Laplace times H is just the equilibrium measure. So you can actually replace this by the equilibrium measure, and this is exactly the quantity that you see here. Okay, so this is, of course, not a formal proof because several things are washed under the carpet, or whatever the correct expression is. For instance, this shift here is, of course, something which has unbounded support. So you have to make sure that you're shifting by something which is still in the Cameron-Martin space, but this is actually the case. Okay, so bottom line is that you have this formula, and in fact, this proof works in the discrete. It works on the cables. There's nothing specific to the cable in what I just said. What I'm going to say now, though, is going to be specific to the cables. So, yeah.
Sorry to interrupt. I'm a little bit confused. Is the sigma algebra the collection of indicator functions phi x is larger than A for each, like the collection of indicator functions for each x and k, or is it just...
Yeah, that's what I mean. Sorry.
But, okay, and then my next question is that the left-hand side of the differential inequality doesn't explicitly depend on k.
But it does, because I'm assuming that my f is measurable with respect to stuff in k only.
But I'm thinking if you fix an f, that it could be, you could take one k and also a larger k.
Absolutely.
And the left-hand side doesn't depend on which k you took, but the right-hand side does seem to.
So I'm going to come back to this in a moment. So it's actually a good question. You could have written k prime here, and the claim is that both right-hand sides are actually the same. And so the short answer to this is that when you work with the equilibrium measure, there is something which is called the balayage formula. which tells you that if you start a random walk according to this bigger equilibrium measure and you just look at its entrance probability in K, then the entrance law is the equilibrium measure in K. And that's how you can see that these quantities on the right-hand side are actually the same. Okay. We will see this actually in a minute. Any other questions? Okay, so I want to apply this now to my percolation problem. So I want to apply this to a function which is going to be a function of my cluster in K of the origin. So this is the cluster of my distinguished point in this excursion set. So I guess I'm still writing tilde after all, which is a dangerous thing, but try. Okay, so if I make a picture here, sorry, I didn't mean to write, I meant to write, sorry, just the cluster in K. So I'm going to make a picture, which is hopefully going to make this clear. So let's say my set K is about, oops, like this. And I don't like this box. Okay, is my pen dying on me now? Okay, that's better. Okay, so this is my set K. This is maybe the boundary of K. So this is in particular the set where the equilibrium measure of K, which is the thing that you saw in this formula, is supported. And so I want to look at a function of the cluster of the origin. So let me draw that cluster. So it's just a cluster in the box K. So it's going to look, so blue was open. So I guess maybe it looks something like this. It may touch the boundary or not. I don't really care. Yeah, maybe let's just leave it at that. So actually here, everywhere you you hit the boundary, and the way that you should view this is that when you explore actually here, you're on the boundary of the cluster. So here as well. Okay, and this is still blue. So everything blue is where my field is bigger than A. And then at this boundary, of course, so here the field is still greater or equal to A, but in this red region, I'm reaching the boundary, a piece of the boundary of my cluster. So here the field is actually equal to A. Okay, but anywhere on the boundary of this region here, sorry, my field is at least A. The region that I'm shading here, this is exactly what I'm calling CKA. And indulge me, I'm going to write this C from now on. Okay, so I have my function that depends only on this randomness that I shaded here. And notice that, as opposed to the sort of discrete picture, the blue and the red line here, they really coincide, right? I mean, this cluster stops when you reach the value A because it's a continuous field. Okay, and now, so what am I looking at in my derivative? So I have my functional of this cluster. This is this guy, and it gets multiplied by this weighted average of phi against the equilibrium measure. So this, if we look at it for itself, is just something that, you know, takes field values everywhere on this boundary. So I'm only drawing a little portion here, but it goes, you know, everywhere along the boundary of K. And so this, you know, you average essentially think of the equilibrium measure as being uniform. If you took a approximation of a Euclidean ball in ZD, that would be, you know, almost true. You basically do an average of the field along the boundary. So this is this. Okay, and so what you can of course do now is use your Markov property. So let me do that. Okay, so I guess what I'm doing is that, you know, in principle, I have to look at this quantity multiplied by my function of my cluster and take the average of this. But I'm going to condition on, so I'm going to put this in quotation marks. I'm going to condition on the field restricted to this cluster C. And of course, you should raise your eyebrows here because C is itself a random set, but the point is that it's a set which is explorable. So in the same way as there is a stopped sigma algebra for, you know, one-dimensional Brownian motion, you can define the stopped sigma algebra that corresponds to the field restricted to this cluster. Okay, so you should think of this sigma algebra as being all the randomness you need to discover this blue cluster C. Okay, so if you just apply the Markov property to this, so again, I'm hiding something under the rug here because, you know, I stated the Markov property, first of all, only for the discrete Gaussian free field, though it also holds for the cable system one. And more importantly, I stated it for a fixed non-random set. And here I'm saying that you should basically apply Markov property with K in the lemma that I was writing in lecture 2 to be, you know, this random set that I chose. And this is basically the strong Markov property that you're in effect applying. And so then this guy splits into, remember, harmonic average plus psi. But if I take an average here, so recall, right? The harmonic average is a measurable function of the stuff I'm conditioning on, and it's some average of the field values that I'm conditioning on. The field psi is completely agnostic, right? It's independent of the stuff that I condition on. And so in particular, if I take an average, as I'm doing here, the average of psi is just going to be 0. So all of this to say that, you know, expectation with respect to psi is independent. So that's 0, and the h is the opposite. It's measurable, so there is no averaging at all. So after the dust settles, you're just left with ek against h. And the conditional expectation has disappeared. And now if you just unpack what this is, well, so there is a sum over the equilibrium measure. And then there is this harmonic average. So what was the harmonic average again? So this was this weighted sum of field values, but you weigh by the probability to actually, for the random walk starting at x, to, you know, enter the set C through y. So this is this probability that you hit the set C that you're conditioning on, and that you hit it in the point y, and then phi y. So this quantity here is hx. Okay, so if you look at this now, so what is this saying? Well, it says that I have my point x, so x is in the support of my equilibrium measure, right? So x is some point here. It could be a point that's blue. That's also possible. Just in that case, the entrance probability trivializes to this point. And then, so you are looking at the probability that the random walk, I mean, the random walk could do anything, right? It could decide to go far away, but you're looking at the probability that eventually you will hit the blue set. So let's say you hit it through here. You could also hit it through, I don't know, here. It doesn't really matter. And then wherever you hit it, you pick up the field value there. But you see that no matter where you hit it, right, whether you hit it on red or blue, this field value is actually greater or equal to A. So overall, what you find is that this conditional expectation is greater or equal to then A times, and now you have the sum, equilibrium measure of X. You can basically sum the Y's, if you like, probability starting from X that you hit C. Okay, and the way, maybe let me write this slightly differently. I'm not doing anything. Is the way you should think of this is that you start a random walk, but rather than starting it at a given point, you start it from the equilibrium measure of the set K, and you look at the probability that it hits this set C, and C is just a subset of K. And now the balayage comes into play. So this is this balayage or sweeping identity, which tells you that this entrance law into the subset C is actually the equilibrium measure on C. So this is just a fancy way of writing the capacity of C. Okay, and just to say, so in this calculation, there is a strong Markov property also for the discrete free field, but in this calculation, I have used crucially the continuous structure because I'm using that on the red part of my explored cluster, the value is really equal to A. If I were in the discrete, then it would jump from being bigger than A to being something maybe slightly below, and that's where this precision goes amiss. Okay, so what have we learned? So we've learned that actually I can write this conditional expectation if I look at a functional of my cluster. I can bound it from below in this way. So, so if I feed this into my differential formula, you're going to get that minus d by dA of some event that depends on my cluster C. So C was my cluster of the origin at level A inside of K. So this is bounded from below by A times same functional times the capacity of the cluster. And of course, when you see this, there is one thing that you want to do is you want to take this functional not to be just a functional of the cluster itself, but just a functional of the capacity. Because if you do that, you get an autonomous differential inequality that depends only on the capacity. So you choose, say, f of C to be, for instance, the indicator function that the capacity, say, lies between two numbers S and T. And if you do this, you now just get a differential inequality for a scalar random variable, which is this capacity. And now if you integrate and you look at this for long enough, so I'll spare you the details, you will deduce that the capacity of the cluster, so I should probably resuscitate the A here. There is a dependence on A. When A is equal to 0 is finite almost surely. So this is just a little bit of algebra, which I'll spare you. You can amuse yourself. And basically, when you integrate this, maybe I can do one step, then you're going to get, so you integrate between A and B, where A and B are two real numbers anywhere on the real line at that stage, then you're going to get something like the probability that the capacity of CB, so this, let me write everything carefully. is bounded by the same probability at level A, and then you're going to get, from integrating here, you're going to get something like B minus A divided by 2. Okay, and then, you may want to start by proving this by not looking at A equals 0, but by A or B, which is strictly positive. Then you can maybe first neglect this probability and show that that this is finite, and then you let B essentially tend to 0. Okay, but that's essentially the end of the proof. Okay, and that proves this theorem. And I think I will stop here.
Thank Pierre. Okay, so any questions?
Hello. Yes. So maybe a question about the Markov property of the extension of the field to the cable. So I guess if you want to prove it from the approximation procedure that you use to define the cable system, maybe it's doable. The question is, I don't know. I see you. Okay. Is it easier if you, I mean, how would you prove it with the definition with Brownian interpolation? Is it a Brownian miracle, or is it something that just comes from the Markov property of the original field?
Right. So I claim that you can essentially run the same proof. So let me not delve into strong Markov, just simple Markov, which is good enough. So there's different ways. Oops, what am I doing? You can do it, but let me go back to the way we proved it in the discrete case. Let me see if I can find the slide. Yes. Is happening. Okay, so there are several ways that you can argue. One is to simply run exactly the same proof if you think about, what plays the analog of what. So I haven't told you this, but if you just think about this K-Bird system Gaussian free field, you might wonder what is the covariance structure of this field. So first of all, I told you if you restrict it to the vertices of your graph, then you have the discrete Gaussian free field again. So whatever this covariance is, it has to be something that extends the original Green's function. And actually, there is a random walk, which you might call now a Brownian motion, that you have essentially constructed in this way that you should think of it as moving around on this continuous structure. And it's a transient Brownian motion because actually it interpolates the discrete random walk, so it's transient in exactly the same way as the random walk was. It's a refinement of it, if you like. And so you can basically run this this argument that I wrote here, just replacing the random walk by this continuous Brownian motion, and that's a proof. And if you don't like continuous objects, you can even devise a completely discrete proof. So if you think about it, like for instance, if your set K is connected, the subset of your cable system, then actually, I mean, if it's say bounded, its boundary will consist of finitely many points. And you can just look at the graph which you obtain from your original graph by adding these boundary points. So you will split some of the edges where these boundary points exist and add these boundary points as midpoints which are not exactly in the middle of an edge. And if you do this respecting network equivalence, so you will put the right weights in such a way that your random walk on this extended graph, its trace on the original graph is your original random walk, then you can basically prove the Markov property on this discrete graph directly. Does that make sense?
Yes. So may I ask a question related to this? So I guess you suggest to, in your first proof, to extend the discrete green function by the inverse of the Laplacian, which is the continuous green function, and then do the same proof with the Brownian motion. Okay, maybe I could. It's maybe a strange question, but maybe I could try to find another extension of this discrete function. I just want to extend the discrete function with, I mean, a function that is defined on, say, ZD to a function defined on RD, which I can do in many ways. So if I were to construct, I don't know, maybe another diffusion that maybe coincides with the, I mean, the generator of which coincides with the Laplacian on Z2, on ZD, sorry, would I have a chance to also get the Markov property?
So that's a good question. In fact, there are natural candidates to do this. So for instance, there are natural generalizations of the GFF which involve, you know, instead of taking a square and your potential, you take some other convex function of the gradients. So this is maybe something that's still relatively close, and there is a random walk representation there. So short answer, I'm not aware, okay, except maybe in some special cases, like for instance, if you do, you know, you could do a field where you're basically averaging Gaussian free fields in a certain way. Anyways, I'm not aware of any example where that really works, but if you want to answer this in any specific case, the question that you basically need to answer is there a natural way to essentially cut an edge into two? If you can do that, then you're in business. So you need to be able to extend your model in a natural way at the midpoint. Yeah.
Any other questions?
Okay, so the capacity is finite. So I guess one natural question is that, can you say something about the expected capacity?
Very good, yes.
In analogy to the, you know, because we'd expect it to be infinite, right? Like in analogous of susceptibility.
Mm-hmm. So, very good question, unsurprisingly. So I've actually only proved so here my goal was to prove that at A equals 0 the capacity is finite. So suppose you have now proved that. I mean, you have, we just did it. So this is now a piece of knowledge. You can okay, and let me put myself in the situation where you know, having finite capacity implies that my set is bounded. So now you can look at this picture again, and so you know that the blue stuff, it will, I mean, it has to be finite. So, you know, eventually you will have explored it all. So what you can do now that you know that this set is finite is to basically, you know, I guess you could call it turn the screws on this argument. So if you now know that it's finite, this is something which you don't know a priori, but we just proved it. And now you let K grow. So you make it grow until it essentially at some point contains all of the red stuff. Then you see that this inequality actually becomes an equality, right? Because the only way you had an inequality rather than an equality is because here you could still continue to explore, and when your yellow random walk hits through here, then the field is greater or equal to A. In fact, with probability 1 strictly greater than A. But when you make K larger, okay, so now I'm going to botch my picture, but I'll try to do it. Okay, so imagine that K is now this set. Okay, now red is everywhere inside. You explore it. Anywhere the yellow thing will hit, the blue will be on a piece of the red curve. And so there you can replace this greater or equal to A by equal to A. And now you actually get a differential equality. which you can integrate, and that means that, you know, the law of this cluster capacity observable is actually explicit. So you can, it's an integrable quantity. Under the assumption that clusters at scale 0 are bounded, which is often the case, but not always. So this is not something which is true on any transient graph. Okay, but you know, it's true, for instance, on any transitive graph. So it's true for a very large class of graphs. And so you can, you know, integrate, compute, and what you find. So maybe I can write this at the bottom here. So, okay, now I need to remember. So I think the probability that the capacity, say at the critical point, is larger than some number s, this decays when s tends to infinity, like some constant, which is explicit, times s to the minus a half. So you actually don't have a moment, which is what you expect. Yeah, you have a fractional moment. And when you want to go from this information to information about what's the probability that you connect to distance r, basically you need to understand how the cluster implements this law of the capacity. Is it rather sort of filigree, or does it become bulky, etc.? So this is, you know, some information, but it's, you know, it doesn't solve all your problems. So for instance, if you want to prove the theorem from lecture 1, you still have work to do.
Okay, any questions?
Yeah, I apologize if this is a very stupid question, but like if you compare this proof to the Hugo and Vincent's sharpness proof, like here you sort of explored the cluster from the origin, whereas in their proof you sort of explore the cluster from the boundary of your
No, you actually do both, right? I mean, you explore from the boundary and you also explore from the origin. And the reason why there is a little mismatch is because, you know, actually right at the boundary, you go from being open or closed. And when you have a discrete model, you have this little jump happening. And this tiny little looking, I mean, it's not that tiny actually, this little deficiency, if you like, which would also be present here in the discrete case, is actually what makes all the difference if you think about it.
Okay, I'll think about it. Thanks.
Yeah.
Any other questions?
Actually, I mean, in a way, sorry, if I can just add a word, if you can, I mean, if you could, you know, refine this particular aspect of the argument, you would be proving theta pc equals 0. I'm not saying this is a good way to think about theta pc equals 0, but this is where the statement becomes a sharpness statement at not more than that. So this is where you need somehow an epsilon of room, whereas here you can just, you know, you have a precise, you see at the end when you run the argument for the second time, which is the thing I discussed when Subhajit asked his question, you really get a differential equality, right? There is no inequality anymore. It's a precise algebraic equality.
Any more? Any on the Zoom? No. Okay, so let's thank Pierre, and also for giving these online lectures and doing so very early in the morning. So thanks, Pierre, a lot.
Yeah.
All right, great. So I guess now's coffee and the end of today, and we meet again tomorrow morning.